some of the new topics. Okay, wait a minute. Yeah, so today I'm discussing about the enhanced oil recovery method using low salinity water flooding, on which we have worked past few years at our lab at IIT Madras. Now, before I start, okay. So our research is primarily focused on various areas of upstream oil and gas engineering, which are primarily gas hydrate, enhanced oil recovery, flow assurance, and of course, drilling fluids and other areas, related areas. And the work that is primarily discussed today is one of my PhD student, couple of my PhD student who has done some work on enhanced oil recovery methods. Now, before I start telling you about what are the, what is low salinity water flooding and etc., I should tell you that, like we have different blood groups. Similarly, we also have different reservoirs, in the world. And even in our country, we actually encounter different types of reservoirs. And these reservoirs are primarily classified into, heavy oil tas, and you also have black oil or light oil, etc. And you can see their, physical appearance that they vary from their composition to a very clear fluid towards like a blackish and highly viscous, oil. Now, different types of oil are actually there in our country. For example, heavy oil like this is available in Rajasthan. The oil like this is available in Karaikal. The oil like this is available in KG Basin, where we get a gas condensate from some of the gas oil wells. And some of these oils are also available in, Gandhar field, say, for example, in Gujarat, right? And their viscosity and density varies significantly as they differ in their appearance and the composition. Now, while we look at the oil, crude oil, we still rely significantly on our, imports. As everybody know now that the oil is still remain the oil, and the oil prices are touching to 120 to 130 barrels due to the recent war. And our import is about 70% of what we require. And this chart shows some idea about where we are and, what kind of reservoirs that we have even in our country. And of course, there are some recent, discoveries of reservoirs in Rajasthan, which indicates that there is a whole lot of oil still there in our country, and we need to explore that. Now, because the oil reservoirs are there past 30, 40 years, we need to, see that how the recovery can be increased. Now, most of these reservoirs, as they are discovered, they are typically young, and they produce oil due to the primary recovery mechanism, and they start becoming matured. Similarly, how we age in our lifetime, right? And as we become age, we start showing problems in our health. So similarly, these oil reservoirs, when we look at, these reservoirs, and as I said, like different types of crude oil that we have, when they start becoming aged, they start showing significant problems in the recovery potential, right? And increasing a 1% to 2% recovery from these reservoirs is still a highly, economically, incentive for oil and gas industry. Because, we are talking about millions of barrels of oil production from these reservoirs. So any reservoirs undergo three primary mechanisms, which talks about primary recovery, secondary recovery, and tertiary recovery. So primary recovery, as I said, like because of the pressure differential, because we are talking about reservoirs which are of the order of 2,000 to 3,000 feet downhole, their high pressure and high temperature conditions, and also the, the compressibility of the oil and gas push the oil towards the production to the surface once we drill the well, right? And this results in a primary recovery, where we talk about 10 to 30% of recovery from the reservoir. And then we start going forward to increase the recovery by means of water flooding, which is also called as a secondary recovery, where we have an injection well, where we inject water, in some of the injection well into the reservoir, and we push the oils toward the production well. And once this secondary recovery doesn't work out, then we go ahead with the tertiary recovery, and we additionally recover about 15 to 20% of oil from these reservoirs. So in primary and secondary recovery, you can see that, we can recover about 40% of oil from most of these reservoirs, and still more than 50% of oil still remains in the reservoir. Now, when we talk about this recovery potential over a period of time, we are talking about in decades. It's not right like a month or so. So the recovery and the second recovery or tertiary recovery can increase the lifespan of a reservoir by several decades. And we have various UR methods, which is very well employed in the reservoirs, which are categorized from the chemical, thermal, gas injection methods. And there are new methods which are based on microbiology, microbial, enhanced oil recovery methods, etc. Right. And we also have gas injection. And nowadays, carbon dioxide injection into the reservoir is getting a traction because of simultaneous CO2 sequestration and recovery of oil from the reservoir. Well, I'm not going to touch upon this area, but what I'm trying to touch upon is a slightly different area of UR, where we talk about low salinity water injection. That is where we have worked past a few years. And that is what I'm going to present today. Now, what is a low salinity polymer flood, or it is also called as a smart water flood for enhanced oil recovery? So what it has been observed is that when we try to tune the salinity of the water, which is injected into the reservoir for recovery. Now, remember, this water is not something that we drink. This is not a potable water. So we do not have to worry about what kind of water that we are injecting into the reservoir. So this is a water that is generally reproduced from the reservoir from the same well or same field, oil field, and that is re-injected into the reservoir. So if you try to tune the water, slightly, tune the concentration of the salt, you can see that there is a significant recovery that can be increased from the reservoir. So you can actually see potential additional salinity, additional recovery due to the low salinity water injection, right? And it has been observed that some of the projects that British Petroleum has done, that they could increase the net recovery by about 700 million barrels of oil equivalent. And that is a significant incentive for an oil and gas industry. Now I'll touch upon some of the basic concepts that what governs this phenomena and what actually the work that we have done so far. Now, this schematic shows that how it looks like. When you talk about high salinity water, the oil droplets are stick to the surface of the rock, right? And because we are talking about not really a tank downhole in the reservoir, but it is a oil that is present in the rock. If you can see my hand, this kind of rock that is available, which are highly tight rock, and the porosity is about 20 to 30%, or sometimes even less than that. And the permeabilities are significantly low. It's of the order of maybe 100 millidarcies or so. And for example, in shale reservoirs, the permeabilities could be even less than 1 millidarcies. So we're talking about such a tight rocks where the oil is trapped into the porous of the rock, which is right there in my hand. And how to recover the oil that is there in the reservoir, right? And if you try to tune the salinity, you can actually pull out some of the oil droplets from the surface and increase the recovery. So before I touch upon the founding principle of this low salinity water flood relies in a paper published by Jones Ray in the year 1937, which observed that the salt concentration, if we try to tune and primarily if you reduce it, it can actually decrease the surface tension of the aqueous system. And this observation is very well reported in the literature. And subsequently, Langmuir in 1938 had refuted this phenomena by Jones Ray, saying that it possibly an artifact and maybe is possibly due to the experimental error or so. However, the Jones Ray effect still holds good. And some of the papers which are published recently, and there are several lot of papers that are being published on this effect, where it has been found that the impurities, does not really impact the decrease in the surface tension of the aqueous system if you try to tune the concentration of the salt. And even some of the papers, shows that even if you add a surfactant, for example, you still try to figure it out that the salt concentration do impact the decrease in the surface tension of an aqueous system. And now you can see that there is a minimum of surface tension, and you increase the salt concentration, then the surface tension start increasing. So there is a whole lot of interaction that goes at the surface of the water when we increase the salt concentration. And this Jones Ray effect, what was reported in 1937, was primarily focused towards the surface tension phenomena. So, however, we are talking about, and of course, they did not thought about enhanced oil recovery or something else, which they did not really thought of, that this might have some implications in enhanced oil recovery. However, it has been observed that when you talk about this, interfacial tension between oil and water, and we talk about salt water or seawater, etc., that is typically being injected into the reservoir, it has been observed that if you try to really tune the surface tension of the tune the concentration of the salts in the water, you can really fine tune the interfacial tension, which actually one of the primary reason by which we can actually recover oil from the reservoir. So if we really decrease the surface tension, we can recover oil. It is similar phenomena that how we wash our clothes, right? You use a surfactant and then try to recover whatever spot that is there on your clothes by decreasing the surface tension. So there are other mechanisms by which low salinity water flood has been reported by various literatures starting from 1999 to 2010, and that really relates to formation fine migration, in situ saponification, etc., and multi-component ion exchange, and salting in effect, and electric double layer expansion, and mineral dissolution. Because there is also clay and sands that is there in the reservoir, and people have come across different types of mechanism which really governs this recovery potential. And of course, not much focus has been done understanding what the wettability really affect, what really the interfacial tension affects the recovery mechanism. So in this pursuit of research, what we have tried is to start understanding a basic alkane and salt interaction, because crude oil is a very complex fluid. You really do not know what's happening there, if you really try to use a salt. So we started looking at pure hydrocarbons like pentane, hexane, heptane, and also try to look at monovalent and divalent salts interaction on the interfacial tension of these alkanes and the aromatics, benzene and toluene. What we observed is that there is indeed a decrease in the interfacial tension of these systems, and there is some concentration which governs the minima IFT for some of these alkanes and aromatics. What we have observed in general is that, and coincidentally, this paper is a relatively a very simple paper. However, we have proposed a mechanism, and this paper in less than 3 years got about 60 citations so far, which really satisfies me. So what we have observed is that the alkane interaction as far as interfacial tension is concerned with the salt water found that the monovalent salt has a more impact on decreasing the interfacial tension of aliphatic hydrocarbons. However, the aromatic hydrocarbons, the interfacial tension found to decrease significantly with respect to divalent salts. And because in a seawater, you have both kind of salt, and also the reservoir, maybe some reservoirs might be aliphatic or some reservoirs might be aromatic. We can try also to tune the salt concentration reasonably, looking at the monovalent and divalent ratio to address the oil recovery potential. So this, mechanism lies in the fact that, looking at the Gibbs isotherm, where it has been related that the change in the interfacial tension is directly related to the excess surface concentration. And it has been said that while we increase the salt concentration, the surface excess concentration increases because the cations goes at the surface and they try to interface at oil-water contact, and they decrease the interfacial tension. However, as we increase the salt concentration, the cations start dislodging from the interface, and therefore the interfacial tension between the oil and water, oil means pentane, hexane, or benzene, toluene, they start getting increased. So this is a simple mechanism that we have proposed related to the Gibbs isotherm. And what this takeaway is that how the salt concentration and the monovalent and divalent salt affects the aliphatic and aromatic hydrocarbons and their interaction. So subsequently, what we have looked at is looking at the wettability. So all the reservoirs, when you talk about the rock, they are primarily water weight in nature, and that increases the oil recovery. But over the period of time, as they become aged, the wettability changes from the water weight to the oil weight. And as an engineer, our target is to reverse the wettability from oil weight to the water weight. So what we have looked at also the impact of the the salt, like a monovalent and divalent salt, and how the contact angle changes between the model oil A and B, which is actually considered as acidic oil and base oil, to simulate some conditions of the reservoir. And what we observed is that the salt concentration, whether it is a monovalent and divalent, does not only affect the interfacial tension of the oil water system, but they also change the wettability from oil weight at higher concentration of the salt to the water weight, and which is what is a desirable for enhanced oil recovery purpose. So here you can see that in both the cases, the wettability changes from say intermediate or oil weight to the water weight condition as we decrease the salt concentration towards minima. Now this is really interesting. That means it's not really recommended to use a high salt concentration, but if you try to tune the salt concentration slightly to a lower value, now here lower value does not necessarily mean that we are talking about 500 TDS or 100 TDS. We are talking about still 5,000 ppm or 10,000 ppm injection fluid, and that's where we are talking about low salinity water. So subsequently, we have looked at how they relates with the IFT and the contact angle, and they have some synergy between them. So as the contact angle, as the interfacial tension also decreases, what we've also found is that the contact angle also changes as the interfacial interfacial tension changes. And what we have understood is that as we look at the monovalent or divalent salt, they typically form the metallic complex or organometallic complex with the oil at the silica surface. For example, that is where we talk about sandstone reservoir, where they are primarily negatively charged, and when we have this cation that comes in relation with the negatively charged surface of the sandstone reservoir, here in this case silica, they try to make a bond or say complex between the oil component. But when you tune this salt concentration to the lower value, the oil component starts detaching out of this silica surface, thereby recovering the oil from the reservoirs. And that is where we talk about low salinity water weight condition, which is a favorable for enhanced oil recovery system. Now we have done some studies again to look at, we got a seawater from the Marina Beach, and we tried to tune the water, say 50% dilution, 25% dilution, and 10% dilution. And we did some experiments which mimics the reservoir in field. What we observed is that using the different combination of the seawater, if you try to tune the concentration differently, like 50, 25, and 10%, and we use the crude oil from one of the field from Kraikal, thanks to Oil and Natural Gas Corporation. We got the API gravity of the oil is about 39, which is relatively a thick oil, not really thick. I mean the brown oil, and the viscosity and so forth are provided here. What we observed when we really did some work on recovery using this oil, we first looked at the interfacial tension of oil water system. Now we are talking about crude oil, so we started with a very pure hydrocarbon like alkane and aromatics like benzene and toluene, understood the basic principle that governs this change in the interfacial tension and so on and so forth. And we also looked at the wettability. Now we have looked at the actual crude oil that is coming out from the field. And what we observed is that when we talk about interfacial tension and when we try to tune the concentration of the seawater, to a dilution of 50% and 25% and 10% dilution, what we observe is that there is change in the interfacial tension, and one can see that there is a decrease in the interfacial tension of oil water system at say minimum value. And again, you further decrease it, the oil water IFT start increasing. There is no point of further decreasing it to 5% seawater, because that really becomes a potable. That's not really something that we intend to. Now, we also looked at the contact angle impact. Contact angle that relates the wettability of a reservoir rock, as I said. Now, this wettability shows that it starts about oil weight condition when you use a seawater, and as you dilute it further to 50% seawater, it comes into the intermediate weight rock conditions, and as you further dilute it to about 25%, it actually converts into the water weight condition. Now, as I said, like water weight reservoir rocks are favorable for enhanced oil recovery, because initially by nature the rocks are actually water weight in nature, and because as they age, as they produce oil over a period of say 20, 30, 40 years, the heavier hydrocarbons remains there in the reservoir, and they alter the wettability from water weight to oil weight, and thereby decreasing the recovery. And therefore our intention is to recover the oil by altering the wettability, and which indicates that if you try to tune the seawater concentration at an optimum level, you can actually not only recover the oil, but also alter the wettability. And that is what we found it doing some experiments. As I said, like we have a setup and we do some experiments. What we observed is that additional oil recovery can be observed to be about 8% when you have a 25% seawater injection. Now, this is a lab investigation, right? We are talking about reservoirs which are about 500, 600 acres and, more than that, right? So there are a whole lot of things that goes in when we really take these, studies from lab to field, where we do a reservoir model and we do simulates, understands the reservoir heterogeneity and so on and so forth. But however, these lab studies actually are a precursor to take it forward and understand the potential of any recovery method for oil recovery in actual oil field conditions. Now, when you talk about 10% seawater or 50% seawater, they observed to recover less oil, though they shown some recovery, but still it shows that 25% seawater had provided a significant recovery at the lab condition, and which is still, very encouraging result. Now, in pursuit of further, improving the performance of this low salinity seawater, we have actually now been looking at how the nanoparticles can be, explored for their recovery. And what we have done is that we have actually used different types of nanoparticles, and these are again silica nanoparticles or kaolinite based nanoparticles. What we observed is that when we form these nanofluids of nanoparticles in low salinity seawater, where we have now referred in the literature, and we are one of the first one to refer that as a smart low sal fluid. What we observed is that when we form these nanofluids, say for example 2000 ppm of a nanoparticle, and these are actually a core sample that I have shown you in my hand, right? So these are outcrop of a reservoir rock, and when we try to saturate it with the crude oil, and if you use a deionized water just as a base fluid, we see that not much oil is coming out from the deionized water. And when you use a low salinity water,
Jitendra, we have consumed 20 minutes. Thank you.
Yeah. So when we use a low salinity water, we could see that some oil is coming out from the rock. And when we use a nanofluids, you can see the rock surface is very white and the oil is actually literally coming out from the rock surface. And the oil recovery studies also show that when we use a nanofluid of these nanoparticles in low salinity seawater, we can actually see improved recovery from the outcrops, reservoir rock outcrops. And there is, of course, relation with when you talk about the contact angle, how the wettability changes. You can see the change in the wettability or contact angle and how the recovery increases for some of these studies that we have done. And that's really, recently published, last year. And right now, what we are looking at in a microscopic investigation, where we talk about rock on a chip, where we have a microfluidic chips which mimics the actual rock conditions. So these are highly random rock matrix. You can see the grains are here, and there is a oil that is present in this microfluidic chip, and that is where we try to flood the different types of injection fluid, like a low salinity water or smart low sal, which consists of the nanofluids or nanoparticles, and we could actually observe that the oil is really getting out from these rock matrix, using a rock on chip mechanism. And this is an ongoing work, and hopefully we'll be submitting a manuscript out of this work very soon. And that is where we are right now as far as this work is concerned. And we are grateful to our various collaborators, not only from academics but also from industry, starting from Schlumberger, ONGC, Total, etc., and various academic collaborators, not necessarily as a part of this work, but the other work that we carry out in our lab. And thank you for my all my PhD scholars, who are actually one of my backbone for the research. Thanks.
We are having some time for discussion. Thank you. It's indeed a pleasure to see that really high quality, industrially relevant, nationally relevant work is being carried out, which makes us self-reliant. So that's great thing to see. And it's also a pleasure to see that it is mostly chemistry. So that's also a pleasure to see that from my perspective. Let me ask one question and pass it on to others to ask what they feel like. Really, to understand oil on the interface, you need to study oil at the interface at the pressures that are required.
Yes, exactly. Yes. Yes, I agree that. In fact, I have built one setup right now where, so measuring the interfacial tension at much higher pressure requires some sophisticated instruments, and those are really costly. We need a PVT cell, pressure, volume, temperature cells, and those one cell cost about like 1.5 crore or 2 crore. And now, right now, I have built one small setup which is a custom made where we are trying to understand the contact angle at oil-water interface using some kind of pressurized equipment. We are still working on it. The question is that how to make a bubble drop, and that's really needs a specific mechanism, and we are still struggling out to develop that. Right now, we have that setup in our lab, and we are not yet successful to push it forward.
Yeah, so what I wanted to say was that studying interface at high pressures, both from a chemical perspective, from a physical, interfacial, rheological perspective, thermodynamic perspective, would be the best thing to do.
Exactly. I agree.
Best thing to do can also be at a microscopic level because droplets are very tiny. Exactly. But that's another interesting connotation that micro droplet, micro science of these thermodynamics of these need not necessarily be the bulk. And ultimately, they contribute to the kind of phenomena that you have. Now, this kind of science, to allow many of these things happen in our laboratory too, where we probe these with spectroscopy. So the interface is probed with a laser or whatever that you may have as a tool. Photon is the only tool that one can probably penetrate at in matter, not electrons or something else. So one is this way. Maybe there is a need to look at interface at high pressures with the kind of insights that you have already got on realistic systems. This is where some new direction can happen, is all that I wanted to say. Exactly. Now, the second point in this context is the interface around this is ions. Well, as you have also studied, and potassium, magnesium and sodium, etc. These ions, their hydration is what happens. They're not ions, they're hydrated. Exactly. So these hydrated fellows at interfaces at high pressures behave quite differently. Need not necessarily be as ions, and what happens is a question that nobody knows.
Exactly.
So that's the other dimension. I leave it there, and thank you. Very nice. And opens up a lot more thoughts, and probably for 50 years worth of research can be done on all of these. Yeah.
Yes.
If there are other questions, go ahead, please. So I don't see other questions. So let me just continue on. What about when you start lowering temperatures or increasing temperatures, the phase behavior around it? Do you think that is a significant aspect? Will some crystallization occur? Could there be other phenomena that can be there?
So typically the reservoir temperatures are much higher. We're talking about 80 to 90 degrees centigrade or sometimes 100 degrees centigrade at reservoir at under high pressure conditions. So we talk about the reservoir. So the temperature may play a role where when we have a dissolved gas there. So, because we are using a crude oil for the lab studies. Now, there are types of oil that we can use it. Where we talk about live crude oil, where we do a sampling in the reservoir and take a live crude oil where we have the oil along with the gas that is dissolved. So the gas oil ratio is significantly high in some of the reservoirs. So for the lab studies, we use a dead oil, and that's still reasonable. But to be precise, and to be more accurate, one need to do studies on the live crude oil and possibly there might be some role of crystallization that may affect. Particularly, we talk about asphaltene content in the oil. So here crystallization, here I refer to the asphaltene, which are one of the highly polar components and very complex molecules that may come out from the oil and may come at the interface along with the ions or so-called from aqueous. So they may play a role also there, where of course, as I said, like that needs a different angle to look at.
Very good. Let me just stop with one more question. That is, your observation of aliphatic versus aromatic species coming out differently, so-called some kind of a chromatography, if I may say, with ions is an interesting thing. What happens? So that precisely says that the way in which hydrocarbons and aromatic and aliphatic hydrocarbons interact with the minerals or rocks or crystallographic surfaces, there is a distinct surface structure. Surface structure. That surface structure is penetrated by your ions in whatever way that is. So that is again a spectroscopy problem to look at. Do you understand why molecularly this happens? That is my next thought on that.
Certainly. I accept. Yeah, whatever you said is exactly right. And of course, one has to look at more spectroscopic understanding what happens, and maybe that is really a interesting way to look at.
Maybe I mean our Rajneesh is also there, and so I mean we can together discuss this particular thing.
Certainly.
Are there other questions, colleagues? Otherwise, we will move on. Well, I don't hear anyone. Thank you very much then, Jitendra. It was a fantastic talk and a lot more opportunities.
Thank you. Thank you, sir.
Right. Next presentation is by Venkatesh Balasubramanian. I'm again not going to introduce anyone. And if you are there, I see VB, right? I see the note as that. Venkatesh?
Yes, I am here. Unfortunately or fortunately, I'm actually not around. I'm traveling, but I'm connected from my mobile. But one of my grad students will do the projection, but we can still carry on with the talk.
Sure. So go ahead.
I'll try to open up my camera, but it's already pretty late at night and it's pretty dark, so I'm going to not have my video on as we go through the talk.
Okay then, so we will have your speech by your student, and you will speak, and he will.
I will speak. The projection will go on by Priya.
Sure. I will alert you after 20 minutes. Yeah, go ahead, please.
Yeah, I'll keep it very simple. Thank you, Professor Pradeep. I'll take it forward from here. Priya, you can go on
so
projection
are you able
mode.
Yeah.
I can see go projection. We all can see. Yeah.
But put it full screen.
Yeah, put it on projection mode. Yes.
Yeah.
Wait. I was actually a little puzzled when Professor Pradeep's office had reached out that how we fit into very serious talks that come, because a large part of the work that we do of late is more from a public policy perspective and things that we try to affect you as things go by. But I'll quickly walk through in the next 5-10 slides, maybe what we kind of do. At some point of time, you can actually see more detailed versions of these talks in or aspects of it in other forums, as well as written about in other areas. So you could reach out on that, or you could reach out to us and we could share those things. So very quickly, to summarize the kind of thing that we do, we work on whatever is the societal demand, so that we can have enhance the quality and productivity of people, process, and products. That's what we work on.
Sir, are you able to hear VB, sir? Audio is cut off for me.
No, I mean, his audio has gone off.
Okay.
Can you guys hear now?
Yeah, we can hear now.
Oh, I don't know when it went off, Priya. Okay,
it went
so
off about 10 seconds ago, 20 seconds ago.
Okay, chalo. Again, we use design thinking approach. We try to solve very complex intractable problems. We use a data-driven approach to solve problems. First, we worked on medical devices. Then we slowly migrated into transportation systems. So how do we improve vehicles? From there, we slowly got into the public policy space, and we kind of drive a lot of road safety initiatives across the country for many governments. I also concurrently hold other advisory positions for some of the governments. So we push the concept of road safety across the spectrum. Priya, roll over to the next slide, please. So, okay, so we, this is kind of the way the journey started, the journey to road safety. It started with concepts of human factors, and then we developed methods. Then we used to drive programs mostly with the industry, whether it's mostly manufacturing, and we were, slowly we got into the process of multiple products. And one of the things that we said that, if a person is there, can we objectively measure how a person responds to environment, whether you are flying an helicopter or riding a cycle or a motorcycle or a car or a vehicle? What do you think? What is the process of thinking? So can we have objective measures and metrics by which we can do the measurement? So that's what we started. So there were quite a few products that went from our lab, patient monitoring system called Nova. Then there was xenogenic material. We had kind of worked on processing polymer, bovine pericardium, which was to fight against the polymeric synthetic materials that were used as patches. And we got into fairly, I think we had one of the best pericardial patches that was made out. Similarly, for anastomosis, that's sold as Synchroscaf. I think that's the only Indian biomaterial that is made from a xenogenic material that's there in the market, as far as I know. And then there is this clamps. One of the people went on to make, one of our students went on to incubate that company, Shira Medtech, which does the Shira clamps. So then there were dental implants and dental clamps that we worked on. And kind of revolutionize the way hospitals are looked at. Should we have beds in the hospital, or bed itself can be converted into the hospital, so that we can have a better perspective and understanding where all measurements, everything, and within a small footprint, so that we could increase the number of hospital spaces and other things. So as we kept drifting, we started working with governments and we started developing program. We put together a trauma care program for Tamil Nadu, which is kind of used as a benchmark across the country, called the Tamil Nadu Accident and Emergency Care Initiative, TAI, which is again all lean manufacturing principles that we started off 20 years ago. We brought it up how hospitals would do the work. So Priya, can you just put where Thai and the apps and other things that are there, the marker, the highlighter? No, go back to that slide only, please. Stay in that slide only. So the idea of it is emergency care is not evaluated at the end of a week or a month or a year. It should be on a daily basis. We collect collate the data on a daily basis. So we develop some apps so can be used in a very very usable format by which by every day 6 o'clock we know the status of 85% of all the trauma cases from whether it is road traffic accidents or emergency non traffic accident cases, emergency cases, anything that is there, we could bring that all up and put it in. So around there, we to develop policies and implementation of policies, we figured out that there needs to be a better way of doing it. So we started something called as traffic accident database Tara that we started in Tamil Nadu, which Government of India adopted, and that went on to be called as the Integrated Road Accident Database. So that's probably the entire country, all the 700 odd districts contribute all. Recently, a month ago or a couple of months back, the Supreme Court made it mandatory as detailed accident requirement. Besides, governments had already come into it. And so we kind of were in that journey. And so Government of India figured out, we're saying that, we were de facto advisors to them in terms of driving a lot of road safety initiatives. So to make it de jure, they, granted very blue sky work. It's not a fundamental research, but not a very restrictive center of excellence, a center of excellence which pretty much decides how it will drive the entire program. So there was a large grant that popped in for us as a center of excellence for road safety, which is where we are at this point of time. Now, why would people think seriously about these accidents, and why would many people, including us, who were doing very serious work in terms of making, the first, our pericardium that we made was much better, not because we made it, but because we did not have any xenogenic material. So if I put my pericardium anywhere, I can allow cells onto the host cells to grow onto the matrix that we put on, or the scaffold that we get. So if I put it in a heart, I grow a heart. If I put it in a scalp, I actually grow hair. That actually happens. So that's the patch material. But of course, it was approved for sales for cardiovascular and neuro. And I think cardiovascular involves also general surgical approach and neuro. So that's where we were using it. Can you flip to the next slide, please? So to get some kind of numbers, we kill about 150,000 people on the roads every year. Now, with data in India, like any other country, you probably don't get the absolute data, because all of you would be very familiar during the COVID season that the fatality count is very confusing. What it is, but this is the declared fatality that was happening, which is 150,000 people. So that's about 4 a minute, I think, is the fatality that we have. And that comes from about 500,000 accidents that happen on the roads, right? So that's actually pretty serious. So this is the recorded one. So the WHO puts it at about another 100K more is the count that WHO says is the fatality, or the World Bank thinks that the fatality, because of underreporting, should be at least 70% more is what they believe. But anyway, with the implementation of that ad and other things, you will have a fairly decent statistic. So the enormity of the problem. So this is the number of people who die. To put more things in perspective, the number of people who die are largely male in the age group of 18 to 57, 16 to 57. That is a very serious age group in which you don't want to lose people. That's the male in the 16 to 57 age group that the fatalities are coming about. Priya, can you just flip to the next slide, please? So we didn't jump in. So I said we use a design thinking approach for problem solving. So how we went about, so when we started the transportation safety framework, we just said, we see so many accidents. TN was leading the country as a pack. We were at about 17,000 plus and climbing on an average of about 10% or so. And we said, if we want to reach a goal that by 2020, 30, we want to reduce 50% fatalities. And 2040, we want to reduce it by another to zero. What do we want to do? So we said, if we apply all our principles of innovation and disruptions, what are the core areas on which we would want to go hack? So the one that we said is all of it is, we said what happens before the accident, what happens after the accident. Come on, if my objective is to reduce the fatality by 50%, I should first reduce the way by which, or rather increase the way by which I improve the survivability of the patients or the victims of accidents. There are often, I know, aggressive, a very good trauma care program. So we had a data-driven trauma care program that was a tie in Tamil Nadu, which I think if somebody goes form by which they are bleeding, we would want to make sure that the guy is saved. And then we have a better quality of life for the person as he comes. So what we call as evacuation to rehabilitation is what we were trying. We were doing a lot of stuff in vehicle engineering. We said we should have various things. So we had this product called IntelliSeat. I think that was one of the first non-vision based IoT enabled ubiquitous monitoring of a driver health and status, and that thing went on to be order component of the year. It was launched in 2017 and 2018. It was order component of the year, but then it's just one part of it. But there are other things that could be done in vehicle engineering, and how do we go forward to get better vehicle engineering and the third is structure engineering that we would want to do. So this is where we started, and then we started taking it forward. Next slide, ma'am. Priya, can you flip to next slide, please? So once we started intervening, at least on the reported numbers, this is the number we saw. Corona, actually, although we planned in 2013, Tamil Nadu had already reached 50% reduction by 2020. 50% reduction vis-a-vis the year of reference, which was the 2016 number. Of course, this is the number that we all go by, and there are other things that people look at and would want to take it. So this is with TN, what happened in TN, right? Priya? So this is again, I think a couple of days back, I think the minister also had mentioned the Tamil Nadu model in the parliament. So this Tamil Nadu model is kind of something that gets spoken about. So it's a bespoke one, which is the idea of the Tamil Nadu model is nothing but a data-driven systems approach to road safety. So that is Tamil Nadu model, and that has been
we have lost you.
People in the meeting today who are there, but these are all the work that we try to do: cognitive and behavioral modeling, socioeconomic assessments, vehicle engineering, and policy interventions that we would want to go. So that is there. So our overall objective is still we would want to hit the 50% reduction by 2030. That is the objective on which we are flying. So I think I'll stop here. Yeah, maybe you can just go to the thank you slide, and we'll stop here. And if there are any questions, we can have a conversation around that.
Thank you. Thank you. Thank you for that overview, and that again shows how our research is contributing to a better country and highly socially relevant program, bring fame and name, and also contribution to society, both in terms of wealth creation as well as real socio-economic benefits. Now, let me ask you, what is the critical issue that we have today in taking this Tamil Nadu model elsewhere, and even in this very same model, what prevents us from going below 50%? You said 50% by 2030. So what are those two aspects? First point is, how do you take it to the nation, and what is limiting? The second is, how can we go beyond 50%?
Okay. So the answer to both of it is we are already taking it to the nation. So that's what we are funded for. We are doing it. So we started with the XYRAD, which is data based on which things it's accident database. So we initially have a data didn't exist, or data didn't exist well by which policy could be driven. So we said first we need to have data. So we started the program called as XYRAD, and that is a challenge by itself. Getting one department to work is a challenge. So we were trying to get 4 big departments in the states to work in tandem. And now we are also bringing in insurance companies, the courts, everybody into it. And that's a mega program that we are, I mean, hope it does get recognized with for this year. But anyway, so having said that, so this is the data, the lack of data, so that can have a data-driven initiatives would have been one of the biggest challenges, and that was getting addressed with the first one. So we had so the second question, limiting factor that should not go beyond below 50%. No, 50% is, and we said 50% by 2030, then it becomes we would want to reach 0 by 2040. Globally, they had a goal that by 2020 they will achieve 50%. I don't think anybody achieved 50% reduction other than probably Tamil Nadu as a country, which had at least officially indicated that 50% reduction was. Globally, they only reached the scale and said 50% we will insert a decade of action from 2010 to 2020 was shifted from 2010 to 2030. So that is a global scenario also. It's largely because there is the behavioral aspects of people, things that contribute towards a failure of accident. So these are all the issues that happen, and that's not a straightforward one. There is a bit of fight that happens to get it in play. So if you were to list the factors, the biggest chunk of it is behavioral. So how does a human behave? Suddenly,
this must be quite a complex thing, obviously.
So that kind of behavioral. It is a very, very complex and
sure.
Have to build a solution, but it's just it sounds like a good rhyming number by which we start and we will be pushing it forward.
Sure. Colleagues, are there other questions? Your talk was disrupted several times because of network connectivity issue and also the vehicular traffic and the noise that is around.
Absolutely. I was, unfortunately, the nature of my work involves me traveling quite a bit. So I'm actually on a field visit at this point of time. So since I didn't get to communicate whether I could join or not, I thought I'll make sure that I'll connect to.
Sure. Thank you. Continue on your journey. Yeah, and it's better that we save more lives. Yeah. That is probably more important.
So bye.
Bye then. Thank you.
Thank you. Then. Bye.
Right. The next talk is by our dear colleague Rajakumar Balla, Professor. Can you please? Yeah, you have already on. Yeah, go ahead, please. I will give you a warning around after 20 minutes or so. Okay. Thank you.
Sure. Are you able to see the slides?
Yes.
Okay. Good evening, everyone. Thank you, Professor Pradeep, for giving me this wonderful opportunity to present what we have done for several years. I thought of taking a problem and discuss that, but what I thought is, well, this is to the general audience. I thought I will present the work what has been focused on for several years, rather than focusing only on a particular problem. That's why the title of the talk is more general, like laser spectroscopic methods in gas phase reactions relevant to the Earth's atmosphere. So here I will give a very, very brief introduction and then go to the spectroscopic methods to describe what kinetics we can do using the laser spectroscopic methods. Just a glimpse of this. We want to worry about this region. Let me put the laser pointer first. Then yeah. So this is the region of our interest, the tropospheric region, tropopause region, and then maybe early stratospheric region. We don't want to go beyond that. All of the parameters are very much well known to all of you. I do not want to spend time on that. So when we do the kinetics of any reactions those are relevant to the Earth's atmosphere, what we need to do is we need to confine our measurements to the pressures relevant to this, that is 1000 millibar to 100 millibar, and also we should confine the temperatures to -40, -50, -60 degrees Celsius. At maximum, on positive side, we can go up to 320. But for the academic purpose, that is the chemistry point of view, we extend up to 360, something like that. But the actual relevance is the window which I'm talking about is this one. Okay. Then, when we look at the chemical composition of the Earth's atmosphere, all this is known to all of us. But the point what we want to emphasize here is, look at the percentage of the CFCs. That's 0.000001. That is 1 into 10 to the minus 7%. Essentially negligible. But unfortunately, they are the most contributors and culprits in the ozone depletion in the stratosphere. And not only that, volatile organic compounds play a very significant role because they do contribute to the formation of the ozone in the troposphere, which is very, very dangerous. And they do contribute to the loss of ozone in the stratosphere in case if they form secondary compounds which actually eat away the ozone. Essentially, for example, the formation of the alkenes, ethylene kind of stuff. Then what happens is ozone gets reacted with this and they lose. I mean, ozone is lost in the stratospheric region because of the secondary chemistry. And the major, one of the key component which we like to emphasize here is methane. We know methane is very, very, high concentration pollutant or greenhouse gas in the atmosphere. Now we talk about the VOCs. All VOCs, what we use today, any compound that we talk is a volatile organic compound, usually. I'm not talking about the inorganic content, but generally more organic content. And then these greenhouse gases seems to be very, very low in the concentration, but they do play a very important role, not only on the global warming, but also on the atmospheric chemistry. So we need to worry about the volatile organic compounds, what happens to them when they are released into the atmosphere. What happens? What happens is when they are raised into the atmosphere through the emissions from the industries or oceans or from man-made Anthropocene contributions, what happens is they get exposed to the sunlight and they form the radicals. Once they form the radicals, the chemistry is on. And the radicals are formed in two ways. One, that is absorbing light directly, depending on the absorption cross sections, they do dissociate if one of the bonds is weak, or they can react with the already existing radicals like hydroxyl radicals or Cl atoms or ozone, O singlet D. You can see all of them here. They can react with, and then primarily the radical is formed. Whether it is a direct reaction or a photolysis, radicals formation is very much essential. That happens. Therefore, we need to worry about how long a compound survives in the atmosphere if it is released. If it is surviving, how long? If it is losing, what are the products? So photophysics as well as photochemistry. Photochemistry part is something, the chemical kinetics and other stuff, initiated, photonically initiated kinetics. Photophysics is something which is really worrisome because if the compound absorbs light, it dissociates into various fragments of the radical kind of thing. Then aerosol formation is initiated, then nucleation of the aerosols, and many other things continues to, it's kind of a chain reaction. So we need to worry about both photophysics as well as photochemistry. So if you want to find out the complete lifetime of the molecule in the atmosphere, the rates of all these processes, like removal process, like dissolution, decomposition, raining out, and the photochemistry, all these parameters, all these processes influence the lifetime of the molecule. Now, in the daytime, what happens is the complete chemistry is driven by OH and HO2. This entire picture represents that. Entire chemistry is cycled around or centric on OH and HO2. That's peroxy radical and hydroxyl radicals. And when you start an organic molecule, and you will see all of them essentially ending towards the formation of either O3 or peroxyalkyl nitrates. And these are the ozone carriers. They go from one place to another place, several of kilometers, tens of kilometers, and then form. Nighttime chemistry is centric on NO3 or NOx related stuff. So we focus on the daytime chemistry now. Nighttime chemistry, maybe at another time I will talk about it. So when we talk about the daytime chemistry, I just want to, out of the context, I want to show one particular slide. This is aerosol, right? The formation of aerosol. Out of the context of this talk, but very contextual to the situation, is coronavirus. You see this? The size of the coronavirus falls somewhere between 40 to 140 microns, nanometers. But the depending upon the nucleation, how long it survives in the atmosphere, they can form, they can be in the size of between 500 nanometers to 1 micrometer. They fall in this region. That's why they are bioaerosols. Okay? Although they are virus, they are in the form of bioaerosols. But this is nothing to do with my talk. Just as a context, I just wanted to mention this. And coming back to the point, when these chemicals are released into the atmosphere, how long they survive? You see, this chemical transport is very, very important. If the compound is surviving for several hundreds of years, for example, CFCs, you see this? CFCs, they survive more than 100 years. And by the time they travel almost 10,000 kilometers. The whole purpose of this slide is if they live long, they travel a lot. And when they travel a lot, and we will have all the chemistry mess in the atmosphere. That's all I wanted to say. So having said this, CFCs are living very long. We don't know how many CFCs, how much CFCs are, what concentration of chlorofluorocarbons are released. Just a glimpse of it I will give you. You look at this. About 450, close to 425,000 of metric tons of CFC, Freon 13 was released. And Freon 12 is about 425. So this is the indication that how much we have damaged the atmosphere. Now, having this in mind, what happens is the chemistry part related to the hydroxyl radicals and chlorine atoms, daytime chemistry. So look at this. When the compound is released into the atmosphere, they react with OH, NO3, O3 and form R dot, R photophysics. And then this radical reacts with oxygen, forms a peroxide radical. And it undergoes various reactions, like reacts with HO2, NO2, and RO2, NO, and all that. You see that finally the formation is ozone. So we may think that only chemicals are destroying the ozone. No, they do form ozone. In fact, the major product is ozone. Essentially, even if the secondary products are formed, for example, if you take ROOH, even if you take alcohol, this also starts as a VOC, and again it forms ozone. So it goes down. The cycle is always to the formation of ozone. So when we release a lot of VOCs in the atmosphere, the ozone formation, we should be as much as, suppose if we are releasing 1 ton of a compound, be prepared to get 1 ton of ozone at one point of time in the troposphere. That is the bottom line. Now, if you look at this, how one can measure the kinetics of these radicals with a molecule, that is important. I am talking about the radical OH radical, okay? The radicals with a molecule of importance in that atmosphere. The best one is pulse laser photolysis, laser-induced fluorescence. And relative rate technique, which I will talk towards the end if time permits, and computational studies we do. So, what is this pulse laser photolysis? I will just tell you. This is the electronic, energy level diagram of the hydroxyl radical. So, if you do this, when you produce the hydroxyl radical, what will happen is we can excite the hydroxyl radical to upper electronic state, and then you can see once the radical is excited to the upper electronic state, what would happen is it would not stay for a long time. It would come down, and it would come down with the energy lesser than the excitation energy, that is 308 nanometers. And then another one is non-radiative transfer, and then from 0 to 0, it forms a 308. That means you know that if you excite the hydroxyl radical, what would happen is it would anyway fluoresce. So when fluorescence is there, when you can excite and stimulate the fluorescence, we can actually capture the fluorescence. You can see this. This is the cell. What we do is we allow a radiation through this and produce hydroxyl radicals, and we allow a radiation through this to excite. This is a perpendicular light, exactly perpendicular four windows, and we send the radiation through this and excite it 282 and see the fluorescence at 308. What does it mean? You have a 248 nanometers, you have 282 nanometers, and also you have 308 nanometers. So how do we detect the intensity of the radical fluorescence? You need to put a bandpass filter about 308, which allows only 308 and captures the fluorescence, and concentration of the intensity of the fluorescence is directly proportional to the concentration of the hydroxyl radicals. So what we do, we are measuring the reaction of a hydroxyl radical with a species of our interest, right? So what we do is we put the species of our interest in this cell, and then generate the hydroxyl radical, and then stimulate the emission of fluorescence by using another laser. That's all we are doing. And now how do we do the kinetics? What is kinetics? Kinetics is, after all, the variation of concentration of a species with respect to time. That's what you need to see. So you probe the hydroxyl radical concentrations at various time intervals, and then see the kinetics. That's all we are doing here. So although I explained in a very simple way. It is very difficult experiment to do, and because particularly in the gas phase. Okay. And now these graphs I will come plots I will come back again and explain a little later. But now, if you look at the experimental setup, this is a jacketed cell. These two are the mirrors windows which allows only probe beam, and these two are the windows which allows only the photolysis beam. And this is the bandpass filter what I was talking about, and there is a thermocouple. However, we have to make sure the detection happens exactly at the center. This is where the PMT is sitting, and with the 308 bandpass filter. So this is the experimental setup, which I will not spend much time on this. But when you do a reaction, for example, I have taken 2-ethoxyethane, and if you take the importance of the compound is it's very widely used chemical and all that. I do not want to get into those, but I will talk about the chemistry what we have done. And you look at the temperature range 278 to 363 Kelvin that we have done. And how did we do? We have put hydrogen peroxide and fertilized at 248 to form the 2 hydroxyl radicals in presence of the compound. Okay. Remember, we do the reaction in the pseudo-first order conditions. When you do the pseudo-first order reaction in pseudo-first order condition, particularly the hydroxyl radical, we keep the concentration around 10 to the 11, and the concentration of the other compounds reactant is about 10 to the power 15. That means 4 to 5 orders of magnitude difference. And then no interference, and you see the fluorescence directly. Okay. Then you see that, and you can ask the laser to photolize at this point and detect it exactly at the point. And after 100 microseconds, 200 microseconds, 300 microseconds, you can increase up to, here we have increased up to 1.2 milliseconds. And you can see various time intervals we have recorded. It is not systematically we have done randomly. And then when you fit the data, this is done exactly. See, you can see varying the concentration, 8 concentrations. C1 is without anything, but when you vary the concentrations by various levels of increase the concentration, what happens is the slope, you see the increase in the slope. And you fit the data, this is for one particular temperature. The next graph shows this is for all temperatures that we have done. When you fit the data, you get the rate curve. It's very simple and straightforward. This is a straightforward experiment where you can 100% rely on your data because we are measuring the optical property. Okay. Now, and if you look at the Arrhenius plot, when you carry out the reaction over temperature range, then you can see variation of the kinetic parameters over the temperature. And we have compared with all that, and I do not want to go into those details of comparison and all, but what I want to say here is, by measuring this kinetics, what are we going to do? We are going to finally, our aim is to find out what is the lifetime. In ambient conditions, the compound will survive for about 20 hours. That means it will be dead before one day completely. That means the radicals are formed in the troposphere itself. They are not going to be transported further. That's all I want to say here. And another thing is, as I told you, these radicals, how do we probe these radicals? You need another spectroscopic technique. That spectroscopic technique is cavity ring mass spectroscopy. And here you can do kinetics, you can do the absorption cross-section measurements, and many things you can do. It's one of the wonderful, finest tool. And you see this? This is a simple spectroscopic technique, but most complicated to handle. This is between a pulse is trapped between 2 highly reflective mirrors, for example, 99.9995% of mirror. Reflective. That means, what does that mean? When the pulse comes here, maximum laser is reflected, only 0.0001% light hits in, and it is trapped because the other mirror is equally bad. Therefore, it goes to and fro, and we are detecting the light at the exit point. These are the red ones are without any sample, blue one is with sample. I have made one animation for all of you. I hope this will be able to work. You see this? How nicely it is. You can see how every time a tiny photon coming out, we are detecting with a photomultiplier tube. And once you do that, you can actually fit the data and with and without the sample. And this is without the sample. As a chemist, I just put the sample over here and then measure the tau. And tau and tau zero, it's a simple Beer-Lambert's law. Nothing much to explain here. But what is that which is very important for you to notice is you have to understand the optical path length before the photon goes down to its natural lifetime. It would have crossed close to 100 kilometers in a 1 meter cavity. That means you can detect the concentrations up to parts per trillion. So that's the whole idea, right? It is like, if you look at the Beer-Lambert's law, absorbance versus concentration versus spaces, it should be straight line. But that is not the case. If you increase the concentration, you see something like this. If you report the data in this region, it is good, but in this region it is absent. So we reduce the concentration to parts per trillion, increase the parts per billion, parts per million, but increase the path length. The reason is the concentrations of the species in the Earth's atmosphere are in the range of parts per million or billion, and not more than that, or even less than that. Okay. Therefore, we use this cavity ring neuron technique to do. I will explain 3 examples. It will take 3 minutes or 4 minutes, and then I will complete. And you see this? This is one of the way. This is called cross-photolysis. All other parameters I don't want to explain, but here this is the probe cell and this is the photolysis cell. And this is cross-photolysis. This is one way of doing the experiment. Okay. The rest we cannot explain in a short time, but in a longer, for a 1 hour talk, yes, I can. But now look at this. The whole idea is we photolyze using 248 nanometers, probe using different wavelengths. Okay. Now this is the cavity ring neuron spectrometer that what we have built. This is the photolysis cross photolysis beam arrangement, and this is for the probe beam arrangement. Okay, everything what you are seeing is designed by us, our students, and we have designed the spectrometer. Software was written and data acquisition was written, and everything is done here except the labels. Okay, it took a long time for me. And then this is another one, is a collinear one. This is for particularly, this is used when the absorption cross sections are weak. You want a much longer path length. That means you have at least the interaction time is very, very long. That's what it is. All other parameters are same. Okay. Now this is the cell. This is a different kind of CRP spectrometer. Now now what we can see is the resolution. If you want to look at this one, 613.8 to 615.8 nanometers. You can see how beautifully you can resolve it. 0.001 nanometer resolution. That means any 2 lines, the distance between 2 lines is 0.001 nanometers. I can use this spectrometer to see through. They resolve it. Okay, and we have measured this. And now another one is a broad spectrum. You can see this orthoxylene we have done, and this is a very broad one. I want to show both, high resolution as well as this is also resolution, but it's no way it's same resolution, but the spectrum is too bad, I would say. Orthoxylyl radical, and when you see this, there is a temperature dependence. You see that absorption cross section is depending on the temperature at which you measure. The decrease of the ground, because of the decrease of the ground state vibrational population as well as the rotational population. This is into the more spectroscopic content. I do not want to touch upon that, but we have seen the variation of the absorption cross section with respect to temperature. The second one I want to explain is kinetics. With that, I will conclude. And see, IO radicals. IO radicals. CLO radicals are the key intermediates in the ozone depletion stratosphere. If you look at the the most famous mechanisms where all the 3 guys got Nobel Prize and all. And if you look at the IO is the next, it's more reactive, but the concentration is less. Therefore, we need to measure this. So we have done this ethanol and ethanol. What we have done is methanol, same thing. See, please understand here. We photolyze and probe. There, what we are doing in LIF, we are inducing the fluorescence and detecting the fluorescence. Here, we are directly seeing the absorption. If you look at the same graphs, they look alike. But what we are doing is there we are detecting the fluorescence. Here we are detecting only the absorption. When the absorption light goes, the intensity comes down, and the photomultiplier tube see the difference. That's what we have done with the various concentrations. And then this is for one particular temperature, and this is when we have combined all of them for all the temperatures what we have done in a particular graph. If you fit this data, you can easily get the kinetics, and you can see the kinetic parameters that we have measured between these. And remember, this looks one simple table, but it's almost take 6 months to 8 months if everything was good. Okay. Now we have done the computational also, which I do not want to get into the details, but I want to explain these 3 are from one particular transition state. This one is another transition state. So we have seen the contribution of both of them, and we can easily see PS2 is this one because of this hydrogen. It's more labile. And then we could contribution would be more. But if you look at the ethyl alcohol, the similar way we have done, and all parameters being kept constant, we have varied the reactant. Okay, that's why these two have gone into one particular paper. And you can see these two transition states are alike, and these three transition states are alike, and this one is independent. So we can see this is again labile, and we can see all the computational details in clear fashion if we have more time. But all that I want to say is the contribution of this hydrogen is more. Okay, and if you look at the pressure dependence and all that, there is no pressure dependence and there is no temperature dependence on the absorption cross sections of IO and all that we have done. And if you look at the Arrhenius parameters, this is for the methyl alcohol and this is for ethyl alcohol. You can see the theory can predict for any long temperatures, but we have the limitation for the experimentation. But within the window of the experimentation, we would say within the given the error bars, these are perfectly fine, both theory and experiment. This is what I want to say. And another very, very simple thing that I will take, Professor Pradeep, one more minute and then conclude, if you permit me. This is not a spectroscopic technique, but we use laser to do this. The advantage with this is a relative rate method. Absolute method, we can see the fluorescence. Relative rate method, what we can do is, it is a static cell. There are secondary chemistry possibilities. But the advantage is, you want to measure the kinetics of A with OH, you put B also. B plus OH is already reported. You take this constant, rate constant, and see the loss of A with respect to B. And compute of course, you measure the concentration of A experimentally, but you compute the rate coefficient for A with respect to OH. But it depends on, the reliability of the data depends on how well the B plus OH was reported. What we do is, we measure B also, absolute method, and then you use a relative rate method. That way we are confident that we are good. The biggest advantage here is you can withdraw the sample here and analyze it in GCMS and GC, and you can actually, I will show you that. You can actually see the products here, and based on the product, you can actually propose the complete mechanism. If this compound is released into the atmosphere, what are the compounds that is going to be formed? And we have GCMS, and we have hyphenated IR spectrometer with the GC. So if we are missing in GCMS, we will get IR, GCIR. If we are missing in GCIR, we will get in GCMS. So it's a complete complement method. And the data, what we got is, you see this, we can get the global warming potentials, we can get the lifetimes, everything as a package. This is what I want to say as a take-home message: is the complete fate of the compound and its potential to form ozone in the Earth's atmosphere can be investigated in our laboratory using super sensitive spectroscopic methods. And this is the lab that it took almost 12 years to 13 years after I started getting the funding. It was not at all easy for me to build these spectrometers. Okay, and then this is the current group. Well, Avinash is not there. All of you know that. At least students would know. He is in Finland, and then rest everyone is here. And thank you all.
Thank you very much, Professor Rajakumar, for that highly emotionally intense and deeply attached presentation. That's quite understandable as well, how passionate you are with your science, and is great. Great to hear this. Let me ask one question and see whether there are other questions that people want to ask. You earlier, we have this tremendously, advanced capability, quite intense atmospheric chemistry being looked at. Now, you also have a possibility of, in the current context, looking at aerosols.
Yes.
And I was curious to know, is it possible to look at atmospheric chemistry in presence of these particles?
Yes, absolutely we can do, but we need a mass spectrometer attached to that, not the GCMS. Particle mass spectrometer we need to attach. Spectroscopically, only we can measure the scattering.
Yeah, but if you are in a position to put these guys inside, let us say these are highly monodispersed particles, need not necessarily be the, let us say, virus or whatever, or atmospheric dust. It can even be a nano cluster, which is not affected by gravity. They are just like molecules.
Yes.
You can put them inside And that is like gas atmospheric, I would say, catalysis on the surfaces of these particles, resembling dust. Maybe at
mimicking the dust, you mean? Yeah.
Yeah.
It can be certainly done if we have the, as I said, we can create these clusters inside the mass spectrometer, and we can easily measure those things.
All right. So that's a I think contemporary problem of great relevance.
Certainly.
That could be looked at. Yeah. Thank you. And are there other questions, colleagues?
And also one more thing is, if you look at because you mentioned the dust and haze, if you look at the Delhi population, I mean Delhi pollution, I think this is highly relevant if we can actually do the nano cluster kind of aerosols, if we can synthesize and we can measure the scattering as well as the masses of those aerosols. Probably that is the best that we can contribute. Let me think about it in that direction.
So the other related material in this context is carbon, graphene or something of that kind. It can even be, need not necessarily go to graphene. There are high quality fullerenes which can be suspended. Fullerenes, fullerols and all that. They will all suspend very well.
Right.
Thank you. And so are there other questions, colleagues?
Hi, Professor Rajkumar. May I ask a question? Professor Pradeep, this is Shiva.
Go ahead.
Hi. So, thanks for the fascinating talk. As you were speaking about cavity ring down, another cavity-based technique came to my mind, which is using frequency combs, which also can really give very high precision spectroscopy. Can do sensing at very high levels. So I'm just wondering, are there ways to sort of maybe combine these two techniques, because both are sort of happening in a cavity? You have superb sensitivity in the case of CRDS, and in the other case, we could possibly do it at multiple wavelengths, like take a broadband laser like titanium sapphire and then use its gain bandwidth to really probe at multiple wavelengths. So, and maybe also look at coherent aspects in the dynamics. Do you think there are possibilities? It's just an exploratory question because there's an exploratory seminar.
Yeah, certainly. That's a wonderful question, Shivam. But there is a limitation with CRDS. If your multiple wavelengths falls in the vicinity of the mirror that what you are using, the bandwidth of the mirror is usually 5 to 10 nanometers. Okay. Above that, it just transmits. Below that, it just transmits. But within the 10 nanometers, the center wavelength, the reflectivity is very, very high, 99.995 or something. But when it is coming down in the Gaussian spray, this one, it can be very, very low. In that case, ring down time goes down.
So it's a limitation of cavity optics.
Yes, optics.
Do I get that
but
right?
As long as the the cavity is the fabriperot, yes, we can definitely do it. And if it's a broadband mirror, if we last week we found a company called LayerTech.
Yes,
they are
I was about to.
Yeah, they are Denmark, I think Germany.
German. It's a German company.
They are giving a broadband mirror which can actually have this reflectivity of 99.99, at least 99 to that point they are giving. I think that is the case. If the window is little longer, let us say, instead of 10 nanometers, if it is 20, 30 nanometers, we can do that.
Yeah, I would vouch for that. And I think for especially two technologies, titanium sapphire based and another is ytterbium based lasers.
Right.
Companies like LayerTech make very high finesse cavities for regenerative amplifiers and oscillators.
Yeah.
So it may be something of interest. In fact, may I just add, even for shorter wavelengths like VUV, cavities are being, at least I see in literature, the reflection-based, reflective optics-based cavities are also being designed. So it may be something very interesting also for the kind of problems that Professor Pradeep alluded to, like atmospherically relevant chemistry, but also at shorter wavelengths. It's just a fascinating topic.
Yeah, but you working in UV is always a challenging thing. The problem is the coatings are usually dielectric components, and they absorb a lot of energy and they go into the deep potential well. They cannot come out. But still we have the mirrors in that. Yeah, definitely we can do that. But there are challenges there. There are challenges, but we are doing in the UV region. You know what is the ring down time constant? You will be surprised. Just 1 microsecond, 2 microseconds, and how much loss we can see. It's very difficult.
Right. Yeah.
Are there other questions, colleagues? I don't see other questions. So thank you, Professor Rajakumar, for that wonderful talk and many possibilities.
Yeah, thank you so much, Professor Pradeep, for giving me an opportunity. In fact, if there are students from other groups, they are most welcome to see the lab. In fact, I encourage you to. It's not because it's my lab. If it's anyone's lab, I think you should see this. That shows the the workmanship of a student, what a student can do. Seriously.
Only students, Rajakumar. Faculty is not allowed to visit.
Come on, Ghosh, you are always welcome. Thank you.
Okay, so thank you all. Thank you for joining, and let us meet next month with another set of presentations. Thank you all.
Thank you, Pradeep. Thank you very much.
Good night.
Thank you all for attending the talk.